Welcome to CECS 228. In this lecture video, we're going to be considering proofs part 3, which deal with induction methods. So there are two types of math induction that we're going to consider. The first being simple mathematical induction, and the second being strong mathematical induction. And so to get a feel for how these types of proofs work, I want you to think of the following scenario. Let's suppose that we have an infinite ladder and we want to determine whether or not we can reach every step of that ladder. We only know two things. We know that we can definitely reach the first step, so you can think of that as a given. The second thing we know is that if we can reach a particular rung, then we can reach the one right after it. So that's the second given. If we were to write a propositional function representing this statement, we could write P of K is the statement, we can reach step K. Then the premises that we've written here, the givens, would be P of 1, meaning we can reach step 1, and that would be true. And the second premise would be, if we can reach a particular rung, then we can reach the next rung. So basically, if we can reach the kth rung, then, or if we can reach step K, then we can also reach K plus 1. And since it's true for any particular rung, it's true in the cases where K is 1, 2, 3, so on and so forth. So the argument that we might try to make then by modus ponens would be the following. As a given, we have P of 1. Also as a given, we have P of 1 implies P of 2, okay, because this is by given 2. And actually, let me go ahead and label it that way. Okay, so given 1 and given 2. Then based on those two premises, if we apply modus ponens, we are going to come to the conclusion P of 2 by modus ponens. And just so that we can keep track of all of the conclusions that we're drawing, I want to say by modus ponens on the first and second statement, and this conclusion will be our third statement. Okay, what next? Well, then I could say, or let me first analyze what this means. This means that we can reach the second rung, and we can reach the second step. Now, we also have as a given that if we can reach the second rung, then we can reach the third rung, right? Because this is true for K being 1, 2, 3, and anything higher. So now if we apply modus ponens on 3 and 4, then we're allowed to conclude that P of 3 is true. Basically, we can repeat this process until we reach P of K or P of N, where N is representing the nth step. Okay, so eventually we're going to reach something that looks like, well, P of N is true by modus ponens on the previous two steps. So therefore, well, actually one more given that we would need. Then we have as a given that P of N implies P of N plus 1. So then we would be allowed to conclude that P of N plus 1 is true, meaning we can reach the step N plus 1. And so let's say that, well, this one's an infinite ladder, right? This one's going to continue forever. So that means that this process would continue forever, but we could eventually prove that we're going to reach every single rung. Now, if it were a finite ladder, let's say that it's just 20 steps, then we could eventually reach 20, right? If n is representing 19, then we would have as a given P of 19 implies P of 20, and then putting these two steps together, we would reach P of 20. And so that's essentially the idea behind a proof by mathematical induction, except that we don't write all of these steps over and over again. We simply say, well, if we can prove that the first step we can reach, or we can say that a statement is true for the smallest possible case in the domain of that statement. And if we can also say that assuming P of K implies P of K plus 1, then it's going to P of K or P of N will be true for every element in the domain. And so that there is called mathematical induction. Now, another way to think about it is as a domino effect. If the first domino is knocked over, meaning if the first statement is true, and if we can show that if the kth domino falls, then so does the k plus first domino, then, or in other words, if the kth statement is true, then so is the k plus 1 statement, then we can conclude that all of the dominoes are going to fall. Meaning then we can conclude that the statement will be true for all values of k or n. Now, in general, when we use mathematical induction, we're now going to be given that P of K implies P of K plus 1. Okay, so in this example, it was given to us, right? This was a given. It won't be the case in most problems where we use mathematical induction, but rather we're going to have to prove that this is true by using some type of method. Usually it'll be by direct method, meaning by assuming P of K and applying some definitions, axioms, other theorems to get to P of K plus 1 is true. Okay. So let's take a look at an example. Actually, before we do, let me talk about what are the steps in mathematical induction. So to prove that P of n is true for all positive integers n, or P of n is a propositional function, we have to first define what is the propositional function P of K for some integer k greater than or equal to k0, where k0 is just the smallest element in the domain. Then we want to prove something called the basis step. Basically, we're just verifying that P of k0 is true. Then we have to show that P of K implies P of K plus 1. That's referred to as the inductive step. So we show that that conditional statement will be true for some arbitrary integer k that is greater than, and this here is a typo, probably doesn't appear on your lecture notes, but it should say for k greater than or equal to k0, which again, k0 is the smallest element in the domain. And finally, the conclusion state, hence by mathematical induction, P of n is true for every integer n that is greater than k0. And when it comes to an actual problem, you don't necessarily want to write P of n, you want to write the statement that P of n is representing. Okay. Now, so any proof that has that you're proving using mathematical induction has these 4 general steps. There is a template that the textbook offers that's a little bit more detailed, and it has 8 steps. So I'll let you guys read this on your own time and use it as a reference whenever needed, but you should know by heart that it has these 4 basic steps. Okay, so let's try to apply mathematical induction to the following problem. They're asking us to show that if n is a positive integer, remember this is read as n is in the set of positive integers, then the sum of 1, 2, 3 all the way to n is the same thing as n times n plus 1 over 2. It'll give you the same result. Adding the first n integers, n positive integers, is the same as taking n, multiplying it by the next number, and dividing by 2. All right, so we said the very first step that we want to take is define a propositional function. Okay, so step 1, we're going to define P of K. So in our case, P of K would be the statement that 1 plus 2 plus 3 plus all the way down to K will be equal to K times K plus 1 over 2. Remember, P of K has to attain a true or false value when you replace a value for K. So it would be incorrect to simply write, oh, P of K is the sum 1, 2, 3 all the way down to K, because that does not attain a true or false value. It attains a numeric value. So just always double check that you have something that can evaluate to true or false, like in this case, an equation. Now we also need to define a domain. Remember, a propositional function always comes along with the domain. So the domain they gave to us, they told us that it has to be for positive integers. So we'll say here for K being greater than or equal to 1. And just to make a note about what type of number, just no decimals, integers only. Okay, the next step. This is our basis step. We want to show that P of K is going to be true for the smallest possible integer in the domain. And the smallest positive integer in the domain in this case is a 1. So we're going to show that P of 1 is true. Okay, so let's give it a try. What is the statement P of 1? Well, P of 1 would be the statement that 1, remember this is the sum of the first n integers. So if n is equal to 1 or K is equal to 1, then I'm only summing over one integer, which is simply 1. And we're saying that that is equal to, replace K with 1, so 1 times 1 plus 1 over 2. Now what is that statement? That's saying that 1 is equal to a 1 times a 2 over 2. And that is true. Thus, P of 1 is true. Okay, what's the next step? Well, the next step is to prove the inductive step. Or the inductive hypothesis. Okay, so the inductive hypothesis is that if P of K is true, then P of K plus 1 will be true. Okay, so prove the inductive hypothesis. So i.e. P of K implies P of K plus 1 or some K. Okay, so it's some arbitrary integer that's positive. So we're going to prove it by direct proof. And in a direct proof, we start by assuming the hypothesis, which is P of K. Assume P of K is true. Now, what does that mean? i.e., we're going to assume that 1 plus 2 plus 3 plus all the way down to K equals K times K plus 1 over 2. Well, we are trying to show that P of K plus 1 is true. And P of K plus 1 would be what statement? Let me just write it here. So we want to show, this is actually something that's very common in some math textbooks, to write WTS as a short for want to show. Okay, so this just means want to show. Okay, we want to show that P of k plus 1 will be true. That's our goal. Okay, we'll just write here. That's our goal. Now, what does that mean? It means, i.e., we want to show that 1 plus 2 plus 3 plus all the way down to a k plus 1 will be equal to a k plus 1 times k plus 2 over 2. Okay, I'm simply replacing in my propositional function, instead of having k, I have k plus 1 now as an input. So it'll be the sum of the first k plus 1 integers, and the result is that it should be equal to k plus 1, because we're replacing k with k plus 1. And then k plus 1 will give us a k plus 2. So that's our goal. How can we get from our assumption to this goal? Well, one thing that we can start doing is we can at least try to make the left-hand side look like the left-hand side of the goal. And what I mean by that is here, if I would have included one term before the k plus 1, it would have been the term adding k. Right, so what I mean by that, let me write it a little bit more neatly. We would be having 1 plus 2 plus 3 plus all the way down to k plus 1 equals this here, because this is the sum of the first k plus 1 integers. So in order to make this left-hand side look like this left-hand side, I'm missing one term. Okay, so I'm going to add that term to the left-hand side of p of k. And maybe it's a good thing to start highlighting soon. So I'll have my highlighter handy. So adding the term k plus 1 to the statement or the equation in p of k, we get the following. We get that 1 plus 2 plus 3 plus all the way down to k plus 1 is going to be equal to a k times a k plus 1 over 2. And I also, remember from algebra, whatever I do to one side of the equation, I have to do to the other as well. I can't just add terms or subtract terms without doing anything to the opposite side, because then the equality no longer holds. Okay, so here what I did was added this term here and here to this expression in the assumption. Okay, now that brings me closer to the goal, right? In fact, I kind of want to highlight this and separate it from the rest of the work, because we didn't really work towards the goal here. We're just stating what we're trying to reach. Okay? So that's what we're trying to reach, and now here's the work. Once I add the k plus 1, I don't have to do anything to the left-hand side because it already looks like the goal. I have to work on simplifying the right-hand side so that it looks like k plus 1 times k plus 2 over 2. Let's see. I'm going to write this as a 2 times k plus 1 over 2 so that we have the same denominator. Okay, so here that's going to be, this is equal to a k times k plus 1 over 2 plus a 2 times k plus 1 over 2. Then when we have the same denominator, we can go ahead and add across the numerators. So that's going to bring us to a k times k plus 1 plus 2 times k plus 1 all over 2. And then I see that both of these terms have a k plus 1, so I'm just going to factor it out. that's going to give me a k plus 1 times a k that's left over from the first term plus a 2 that gets left over from the second term. And then I still have over 2. And then notice what the goal was for the right-hand side. It was precisely that, to get k plus 1 times k plus 2 over 2. So we've shown that p of k plus 1 is also true. So hence, 1 plus 2 plus 3, all the way down to k and k plus 1, oops, is equal to a k plus 1 times a k plus 2 over 2. Which means that p of k plus 1 is true. And actually, I'm going to have to continue that on a separate sheet because I ran out of room. And so this means that p of k plus 1 is true. So i.e., p of k plus 1 is true when p of k is true. So we have that p of k implies p of k plus 1. That is going to conclude our inductive step. Okay, so remember, we were here where we were trying to prove that p of k implies p of k plus 1, and we've reached that. And this is for some arbitrary k. In the domain. So then the final step is our conclusion, in which we state, by mathematical induction, p of n, okay, or p of k, usually once you make it to the last step, we write it as p of n. P of n is true for every integer n that is positive. Now, remember how I mentioned earlier that we usually don't leave it as p of n, we write out what the statement reads. So i.e., 1 plus 2 plus 3 plus all the way down to n is equal to n times n plus 1 over 2. And those are all 4 steps of a proof by mathematical induction. Okay, here's another example. Conjecture a formula for the sum of the first n positive integers, and then prove that your conjecture is correct by using mathematical induction. So let's take care of the first part, the formula. In order to come up with a formula, we need to be able to detect some kind of pattern in taking the sum of the first n positive odd integers. So let's start with just the first odd integer. Well, the first odd integer is just 1, which is equal to itself. There's not much going on there. Then if I take 1 plus 3, which is the sum of the first two, we get 4. If I take the sum of the first 3 odd integers, we get a 9. If I take the sum of the first 4, oops, skipped over the 5, we get 16. And I'll do one more. The sum of the first 5 is 25. And so perhaps the pattern that we're starting to see is that, for instance, when I added 2 odd numbers, the result was 2 squared. When I added 3 odd numbers, the result was 3 squared. 4 odd numbers, result was 4 squared. And 5 odd numbers gave us 5 squared. So maybe our guess is that the formula follows a pattern like 1 plus 3 plus 5 plus all the way down to a 2n plus 1, where 2n plus 1 is representing an odd number. If you recall that from our last lecture, 2n is an even number because an even number is defined as any number that's divisible by 2. And then if you add 1 to an even number, you get an odd number. Okay, so I'm adding everything from, well, 1, 3, all the way down to 2n. Now to determine whether that is going to be n squared or not, let's just kind of see what the pattern is, or what this, for what n would this be true. This would be true, or excuse me, not what n it would be true, but rather for what value of n is this 2n plus 1. It would be for 0, right? 2 times 0 is okay, here's another example, example 2. Conjecture a formula for the sum of the first n positive odd integers, and then prove that your conjecture is correct using mathematical induction. And so I've gone ahead and listed just the sums of a few integers so that we can get a feel for what pattern the result is following, and then try to come up with a formula. So for instance, if I try to sum the first integer, or the first positive odd integer, that is, so n is 1, I simply get 1, right? So 1 is equal to 1. Then when I try to sum the first two positive integers, positive odd integers, that would be 1 plus 3, which gives us a 4. When we try to sum the first three odd positive integers, we get 1 plus 3 plus 5, which is a 9. When we try the first 4, we get 16. When we try the first 5, we get 25. And so what we're seeing, or the pattern that at least pops out to me, is that the sum is always equal to n squared, right? So like for instance, this is 1 squared, this is 2 squared, so on and so forth. Now to come up with a general formula for that, let's think about how we can express the sum. The right-hand side, well, that's kind of easy. That would just be the n squared. But then for the left-hand side of the equation, we want to figure out how we would express that. So we can write it as 1 plus 3 plus 5 plus all the way down to a general representation of an odd number equals n squared. And so to see what that general representation should be, excuse me, we should try and think of these concrete examples. This one, I could write it as a 2 times, and actually let me work over here with this first equation. I could write this as a 2 times 1 minus a 1. This second odd integer, I could write it as a 2 times 2 minus a 1. This third one would be a 2 times 3 minus a 1, 2 times 4 minus a 1, 2 times 5 minus a 1. Okay. And the reason why I'm writing it with minus is because then I see a direct relationship between how many odd integers are part of that expression and the general representation of the last odd number. So what do we notice then? We notice that in general, if you're adding from 1, 3, 5 all the way to 2n minus 1, right, that's the formula that this last odd number has, that the result will be n squared. And so that's going to be our conjecture for a formula. We now have to prove it, and let me just be complete with this problem, with this formula. This is for integers 1 and greater. Okay. So now we have to prove that it's correct. And we're going to use mathematical induction to help us out. So first thing is to define what P of K is. So P of K is going to be the statement that the sum of the first n odd integers, n positive odd integers, is equal to n squared. So we're going to let P of K be the statement 1 plus 3 plus 5 all the way down to a 2k minus 1 is equal to k squared, where where the domain is the set of positive integers. That's our first step. Then we want to prove our basis step, which means we want to prove the statement for the smallest possible element in the domain, which would be a 1. Okay, so P of 1 is true because, well, 1 is equal to 1 squared, right? That's what P of 1 would be stating. It would be stating that 1 is equal to 1 squared, kind of like what we had over here. Okay, so that's true. Then we move on into our inductive step. Actually, let's write it down here. And in the inductive step, remember, there is always the assumption and what is the goal. So the assumption is that P of K is true. And we're going to assume P of K is true for some arbitrary integer k. So i.e., we're going to assume that this statement is true for some random k. Okay, so it's so let's see, plus all the way down to 2k plus 1 is equal to k squared, okay, for some k. That's a positive integer. All right, so we want to show, and this is the goal, I'm actually going to change colors here just so that it's very clear to us that this is not actual work yet, it's just the goal that we're trying to reach. We're trying to reach the goal of showing that P of K implies P of K plus 1 for some k. So i.e., what that means is that we want to show that P of K plus 1 will be true. And P of K plus 1 is true would be the statement that 1 plus 3 plus 5 plus all the way down to 2k minus 1 plus 2k, now we have k plus 1, and then we have minus 1, because remember, this is the sum of the first k odd integers, and then for the k plus 1 plus first odd integer, we would have 2 times k plus 1 minus 1. We want to show that that's equal to k plus 1 squared. Okay, so that's the goal. Now we're going to show some work for it. Now let's think again, how is it that we can go from our assumption, 1 plus 3 plus down to 2k minus 1 equals k squared, to something that looks like this? Well, the goal, the assumption already contains the first k terms on the left-hand side of the goal. we simply need to add this k plus 1 term to the left-hand side and make sure to add it to the right-hand side and then simplify it from there. So we're going to add two times k plus 1 minus 1 to the left-hand side of the assumed equation. And what is that going to look like? Well, we're going to have 1 plus 3 plus 5 plus 2k minus 1 plus this term here, 2 times k plus 1 minus 1 is equal to a k squared plus 2 times k plus 1 minus 1. Again, what we're trying to do here is add to one side, but we can't do it without adding it to the second side of this equation up here. So now if we continue to simplify, left-hand side already looks like the goal. Right-hand side needs a little bit of work. We can simplify what's inside of the parentheses. So for the left-hand side, this is equal to, for the right-hand side, this is equal to a k squared plus, I'm going to distribute the 2, so I'm going to have plus a 2k plus a 2 minus a 1, which is simply a k squared plus a 2k plus 1, right, 2 minus 1. I can drop the parentheses because there's nothing really that I need to distribute, and I would just get a k squared plus 2k plus 1, and that actually factors into a k plus 1 times k plus 1. Right, you can verify by distributing back the terms. K times k will give us the k squared, k times 1 will give us 1k, 1 times k will give us 1k, and then 1 times 1 will give us a 1 squared. So that's a total of k squared plus 2k plus 1. All right, now what does that mean? Well, that means that 1 plus 3 plus 5 plus 2k minus 1 plus 2 times k plus 1 minus a 1 is equal to this k plus 1 squared. Okay, I'm just simply bringing in the left-hand side down here, and we've already shown that the right-hand side is equal to all of this, which is k plus 1 squared. So that actually shows that p of k plus 1 is true. So by a direct proof, then, we've shown that p of k implies p of k plus 1. Okay, so hence, let's write this down. Hence, p of k plus 1 is true when p of k is true, i.e. p of k implies p of k plus 1 for some k that is a positive integer. And so that concludes the inductive step. The final step is to state the conclusion. So by math induction, P of n is going to be true for all integers in the domain, and P of n is the statement that 1 plus 3 plus 5 plus all the way down to a 2n minus 1 is equal to n squared. And this should say for all. All right, let's take a look at example number 3. Example number 3 reads, use mathematical induction that 1 plus 2 plus 2 squared plus all the way down to 2 to the n is equal to 2 to the n plus 1 minus 1. I've already gone ahead and defined a propositional function to represent this statement. I'm letting P of k be the statement 1 plus 2 plus 2 squared plus all the way down to 2 to the k equals 2 to the k plus 1 minus 1. Now what I want you to notice about this problem is that it doesn't have an explicit domain. It doesn't say for all odd integers and or all positive integers and rather. So we have to try and figure out what it is that is the domain for this function. Okay. Now, in order to determine that, we can take a look at what would be the smallest possible case of this statement. If you take a look at the sum, the first term, if we were to break it down to only one term, would be a 2 to the 0. And then we have 2 to the 1, 2 to the 2. So that means that 0 is really the first n value that we can have in this statement. So that means that for the domain, we're going to be considering all non-negative integers. And so that would be, we could just write it as non-negative integers. Later on, when we discuss basic data structures, we'll see how to write that notation more compactly. But for now, we'll say it's non-negative integers and continue on to step number 2, which is to show the basis step. So for the basis step, we want to prove that P of 0 is true. Okay, so P of 0 is true because, well, what would P of 0 be saying? It would be saying that 1 is equal to 2 to the 0 plus 1 minus a 1. And, well, if we check that out, 1 is indeed 2 to the 1 minus 1, because 2 to the 1 is simply 2. That's true. So P of 0 is proven. Now let's show the inductive step. For the inductive step, we're going to assume P of k is true. For some positive, or rather for some non-negative integer k, so for some k greater than or equal to 0, where k is an integer. So i.e. this means that we're assuming the statement 1 plus 2 plus 2 squared plus 2 to the k is 2 to the k plus 1 minus 1 for some k. What do we want to show? Well, the goal is to show that P of k plus 1 is true. Okay, the goal is show P of k implies P of k plus 1. And so in order to show that, we have to prove P of k plus 1 is true. Now to prove P of k plus 1 is true, we need to know what P of k plus 1 looks like. That would be the statement that 1 plus 2 plus 2 squared plus all the way down to 2 to the k plus 2 to the k plus 1 is equal to a 2. Now remember, in this original statement, we're replacing k with k plus 1. So that means this is a k plus 1 in the last term of the left-hand side. And on the right-hand side, this has to be a k plus 1 as well. So it would be a 2 to the k plus 2 minus 1. That's what we want to show. That's our goal. let's give it a try. How do we get from the assumed expression, the assumed statement, to this goal statement? Well, in the assumption, we're missing this last term, the 2 to the k plus 1. So I'm going to add that to both sides of the equation. So adding 2 to the k plus 1 to both sides of the equation assumed true, we get the following: 1 plus 2 squared plus 2 to the k plus 2 to the k plus 1, that's my added term, is equal to a 2 to the k plus 1 minus 1 plus a 2 to the k plus 1. That's my added term. And now if we try to simplify it, the left-hand side, there's nothing more that we can do. It already looks like the goal, but the right-hand side needs a little bit of simplification. So I'm going to add these two terms together because they are like terms. This is kind of like having, let's say like y minus 1 plus y, right? If we had an expression like this, we would say, well, that's a 2 times y minus 1. So in this expression, we have the same thing, but except that instead of y, we have 2 to the k plus 1. So this is going to become a 2 times 2 to the k plus 1 minus 1, okay, combining the like terms. And then we can apply our power rule here since we have the same base. When we have the same base, add the exponents, and that becomes a 2 to the k plus 2 minus 1. So what have we shown then? We've shown that 1 plus 2 squared plus all the way down to a 2 to the k plus 1 is equal to a 2 to the k plus 2 minus 1. Or in other words, p of k plus 1 is true when p of k is true. So that concludes the inductive step, and we can make our final remark. By mathematical induction, p of n will be true for all non-negative integers. That would be the whole proof. Okay, so we're going to take a look at example number 5 now, which is asking us to use mathematical induction to prove that for every non-negative integer n, 7 to the n plus 2 plus 8 to the 2n plus 1 is divisible by 57. So first let's talk about what it means for a number to be divisible by 57. A number is divisible by 57 if it has 57 as a factor. So for instance, 177, we can divide by, 171, if we divide it by 57, it will give us 3. So what that means is that we can actually write 171 as 57 times 3. So in general, what this is stating then is that for every non-negative integer n, 7 to the n plus 2 plus 8 to the 2n plus 1, will be equal to 57 times some integer. Okay, so I'm just going to write that down. In general, we need to prove that for every integer that's non-negative, so n greater than or equal to 0, there will exist some integer k such that 7 to the n plus 2 plus 8 to the 2n plus 1 equals 57k. So that's what we're going to work on now, starting with our propositional function. We're going to let P of k be the statement. And actually, since I've used k here, since we've been using k for the propositional function, I'm going to go ahead and change this to maybe like q. That way there's no confusion between this integer that's being multiplied with the 57 and the variable k that's part of the propositional function. Okay, so I'm going to let P of k be the statement, there exists some integer q such that 7 to the k plus 2 plus 8 to the 2k plus 1 will be equal to 57 times q. And let's not forget about our domain. This is supposed to be true for every positive, for every integer that is non-negative. And then that defines our domain. Our domain will be all non-negative integers. Here's step number 2. We're going to prove the basis step. And since we're talking about non-negative integers, the smallest possible element of the domain is p of 0. So p of 0 is true because, well, what is the statement p of 0? The statement p of 0 is that 7 to the 0 plus 2 plus 8 to the 2 times 0 plus 1 will be a multiple of 57. Yeah, so let's check what that gives. That is true because 7 to the 0 plus 2 plus 8 to the 2 times 0 plus 1 is equal to a 7 squared plus an 8 to the 1, and that'll be a 49 plus an 8, which is a 57. And that in turn we could write as a 57 times 1. So it's true because the number or the result is 57 times the integer 1. Okay. So in this case, q happens to be 1. Okay, but the end of it is that p of 0 is true. Let's try to prove the inductive step. We're going to start by assuming that p of k is 0. And that means that there exists some integer q such that this statement is true. So such that 7 to the k plus 2 plus 8 to the 2k plus 1 is equal to 57 times k. Now, what is our goal? Well, the goal is always to show that p of k plus 1 is true. And so we must show p of k plus 1 is true, so i.e. that there exists some other integer, so let's just call this integer t, such that 7 to the, now k plus 1 plus 2, so that would be k plus 3. So such that 7 to the k plus 3, and then plus 8 to the, if this is a k plus 1, essentially what we have is 2 to the, 2 times k plus 1 plus a 1. So that's, I'll do some side work. If we have 2 times k plus 1 plus 1, that's a 2 times k plus 2 plus 1, or in other words, a 2k plus 3. Yeah, so it's going to be 8 to the 2k plus 3 is equal to 57 times t. Yeah, that's the goal. To show that there is such an integer. Right, so let's work with what we have as an assumption. We need to make this equation look like, at least the left-hand side, look like 7 to the k plus 3 plus 8 to the 2k plus 3. And so here's, by trial and error, you can try several approaches, because this one is not as straightforward as the other examples that we were considering. But for this example, what we can do is maybe multiply both sides of the equation by 8 squared, because doing so we would have an 8 to the 2k plus 1 times an 8 squared, which means that when we add the exponents together, we'll get a 2k plus 3. Okay, so this is what I mean by this. By assumption, or actually let me just say multiply both sides of the assumed equation by 8 squared, and we're going to obtain the following. We obtain a 7 to the k plus 2, and then 8 to the 2k plus 1. And what I'm saying is multiply both sides by this 8 squared. So we get, this is equal to 57 times q times 8 squared. And then when we distribute, we'll have a 64 times a 7 to the k plus 2 plus an 8 to the 2k plus 1 times an 8 squared. I'm intentionally not writing it as a 64 here because I want to keep the same base so that I can add the exponents. And then here what I'll do is I'll simply write this as a 57 times, let's say u, where u represents 64q, and of course is an integer because q is an integer. So if you multiply two integers together, you're going to get some integer. What can simplify after that? Well, we'll have a 64 times a 7 to the k plus 2 plus an 8 to the 2k plus 3 is equal to a 57u. And that was really the reason why I multiplied both sides by 8 squared, because at least I have this one term that looks like what's in the goal. And the right-hand side also looks like what's in the goal. It's 57 times some integer. The part that still needs some work is this first term, because it needs to look like 7 to the k plus 3, and currently we have a 64 times the 7 to the k plus 2. So let's work with that term for a moment. The trick here is to write that 64 as a 7 plus a 40, actually plus a 57 times a 7 to the k plus 2, and then just bring down the rest of the terms. And now what? Well, now we can go ahead and distribute. If we distribute the 7 to the k plus 2, we'll end up with a 7 to the 1 times a 7 to the k plus 2 plus a 57 times a 7 to the k plus 2. And then the remaining terms we bring down. All right, now because these two have the same base, we can add the exponents together, and we get a 7 to the k plus 3 plus 57 times 7 to the k plus 2 plus 8 to the 2k plus 3 is equal to a 57u. Now notice how close this is to the goal. The goal was to have 7 to the k plus 3 plus 8 to the 2k plus 3. I have those terms present here. The only one that's kind of throwing off the left-hand side is this 57 times 7 to the k plus 2. So what I'm going to do is I'm going to subtract this term to the others from both sides so that on the left-hand side it no longer appears. And when we do that, we'll have 7 to the k plus 3 plus 8 to the 2k plus 3 is equal to a 57u minus a 57 times 7 to the k plus 2. Okay, what's next? Well, after that, we can factor out a 57 from the right-hand side. So meaning we could write this as a 7 to the k plus 3 plus 8 to the 2k plus 3 is equal to a 57 times a u minus 7 to the k plus 2. And what's nice about writing it this way is that we know this is an integer, right? U was 64 times q, so it's an integer. And then 7 to some power, or well, some integer power, because k we know is an integer as well. It's a non-negative integer. This is also going to be an integer. So if we take the difference of the two, we're going to get an integer result. So we finally get that 7 to the k plus 3 plus 2 to the k plus 3 is equal to, and I think I actually, let's see, is that, yeah, that's correct, is equal to 57 times a t, where t is the difference u minus 7 to the k plus 2 and is an integer since u and k are integers. So that shows that p of k plus 1 is true, right? Because p of k plus 1 being true means that there was going to be some integer such that the sum of these two terms gave you 57 times that integer. And we're finding what that integer needs to be. It needs to be u, which is 64 times q, where q is whatever integer is found here under the assumption. And then minus 7 to the k plus 2, which will be an integer as well. Okay, so hence p of k plus 1 is true when p of k is true. So i.e. p of k implies p of k plus 1. All right, now for the final step. The final step is to simply say, by mathematical induction, p of n will be true for all non-negative n.